G sub x. That is why it is conservative. So being able to identify whether a vector field is conservative or not is extremely easy. You just need to take the symmetric derivative of each component and see if they equal each other. Okay? And we have this example. Minus yx. This is my f. This is my g. F sub y is equal to minus 1. G sub x is equal to 1. Am I right? This is f, this is g. Taking the partial derivative of g with respect to x, I'm getting 1. These two are not equal, and that's why this is not a conservative. Right? We did try to find its potential function, but we failed. And this is actually the justification of why you can never succeed. Okay? There's no way you can succeed. If you want to make it work, I have to make a y x. So this is indeed a conservative. This is not conservative. This is conservative. Okay? So this formula is extremely practical to find whether a given vector field is conservative or not. So this is not conservative. So let me give you a couple of examples. We can immediately apply our. So let's see this one. If I have a function defined by 4x cubed plus x1 minus x squared divided by 2 plus 2y cubed. Okay? I want to see whether this is conservative or not. By definition, if it is conservative, I'm supposed to find a potential function such that this is equal to the gradient vector field. But that is a much more difficult way to check. Right? If you cannot find it, maybe a third person come out and they can find a potential function. So finding a potential function is not the way to check. However, this is the way to check. Right? This is the way to check. Which means I let this to be my f, this is to be my g. So x component taking y derivative. Y component taking x derivative. So f taking y derivative, I'm getting a x. And the g, I'm taking x derivative, I'm getting a minus x. So they're not equal. So this is not conservative. See, that's pretty easy, right? As long as you can take the derivative, now you have another skill in your arsenal. So you can fire at any given vector field by simply taking derivatives in the correct order. Okay? X component taking the y derivative, y component taking the x derivative. Check if they're equal. If not, immediately this is not a conservative. If it is, I would say usually it is conservative. In this class, it is always. Okay, so there are weird examples if you go beyond capital class. And even if the equation is true, but still it fails to be conservative. But in this class, it is always conservative. And if it is conservative, that means you should be able to find its potential function. This potential function is phi is equal to x squared plus y squared. This guy, phi is equal to x y. Then you take the x derivative, you got a y derivative, you got x. In fact, the potential function is not unique. The potential function is not unique because the only thing I need is take the derivative equal something. Derivative of any constant is equal to 0. So adding a constant here will not hurt the potential function. All right? Yes? If I have a potential function, I change it by any constant, then taking the derivative, it's still going to be a same vector, a gradient vector. All right? So you can add any constant here. This one, it is not conservative, which means there's no way I can find the potential function. So next thing I want you to be able to do is the following. First of all, I should be able to check whether a vector field is conservative. If it is not, my job is done. Okay? If it is, I should be able to find its potential function in a uniform way, regardless of what formula it is. But before that, I wanted to quickly fix this one. Okay? Quickly fix this one. That's just so if I have a vector field in R3, I want to find a similar checking procedure over there to see if a vector field is conservative or not. I still use the same formula. If I have a scalar function phi, I take xz should be equal to phi zx. All right? The second order derivatives, I interchange the order. This should be equal. I would think.
That wasn't dependent on anything though, you just chose xz, right?
Yeah, I just choose xz because I have x, y, z. Eventually I have to use all the pairs. So I'm just taking the pair xz. I'm taking a pair of xz. These two second order derivatives should be equal, which means I'm taking the z derivative to x and x derivative to z component. So similar procedure is also true in R3. So the x derivative of z component should be equal to the z component of x derivative. Okay? So f of x should be equal to h of z. So if I have phi yz is equal to phi zy, so my g of z should be equal to h of y. So phi xz xy is equal to phi yx. This will give me f of y is equal to g of x. So these three equations together will be how you check a vector field in R3 is conservative or not. You have to be able to check all of this. You have to be able to check all of this. Okay? So if a vector field in R3 is conservative, then I'm looking at these three components. I combine x and z component, I take in the symmetric derivative. I take an xy component, I take the symmetric derivative. The yz component, symmetric derivative. Three pairs. You have to check three symmetric derivatives, whether they match or not. Three components have to be all matching in order to make it is conservative. So I want to give you one example here. So let's say I have this part, 3x squared, 3y cubed, and minus 6 is a cubed. This is a very easy vector field. Very, very easy vector field in terms of checking whether it's conservative or not. Okay? I can immediately say this is conservative. X component only depends on x, y component only depends on y, z component only depends on z. This is the nicest vector field. Because remember, in order to check it is conservative, you have to take the derivative with other components to check, right? You have to do the symmetric derivatives, which means if I make this to be f, this is to be t, this is to be h. So fy, I want to compare this x and the y component. Fy is equal to 0 is equal to g of x. All right? So I'm looking at these two. So if I'm looking at, say, these two, which means g of z is equal to 0 is equal to h of y. And if I'm looking at these two components, x and z, so I need a f of z is equal to 0, which is equal to h of x. Okay? So they're all equal to 0, which means this is a conservative vector field. This is a, yeah?
On your symmetric equation, it says f of x is equal to h of z.
Oh, I slightly changed the order, but you have to verify the three.
I think
fc equals h.
So
No, the other one is wrong.
The other one, okay.
So
Yeah, this is true.
The first one.
The first one, yeah.
C.
F of z is equal to h of x. Yeah, thank you, yeah. Exactly. Thank you for pointing that. Okay. Now, all the functions I give you, in order to check it is conservative, is quite easy. But the conservative vector fields, finding its particular function is not challenging either for this guy. Because x, y, z are completely independent. In fact, you can find the antiderivative separately. Remember, because you have to have a function, then take the derivative equals these guys. So So essentially, finding the potential function is sort of like finding the antiderivative. Wouldn't you agree? Right? Essentially, generally speaking, you're taking derivatives. So finding the potential function should be sort of like finding the antiderivative. These guys, x, y, z components are completely independent. I should be able to find the potential function by finding the antiderivative separately here. Okay? So finding the antiderivative here is x cubed plus this guy is equal to y4 3 divided by 4. This guy is minus 6z2 4 divided by 4. And I can add any constant I want. So phi is equal to this guy. This is indeed the potential function. You can easily check it satisfies the gradient vector equations. You take the x derivative, you got the x component. You take the y derivative, you got the y component. You take the z component derivative, you got the z component here. So this is indeed the antiderivative individually, and that serves as the potential function. Okay? What is even much more general is you have these components to mix with each other. And that is what I want to talk next. So let's say if I have a vector field, y plus 2z, x plus 2z, 2x plus 2y. I want to check if it is conservative or not. If it is conservative, I want to find its antiderivative, or I want to find its potential function. So this is f, this is g, this is h. Okay? So let's do a couple of coupling here. So f y is equal to 1, which is equal to g of x. All right? Fy is 1, g of x is also 1, so check. So let's say f of z is equal to 2, which is equal to h of x. So this is also check. Yes? Mm-hmm. So I want to have g of z is equal to 2, which is equal to h of y. This is also check. So this is indeed a conservative vector field. Now I want you to find the antiderivative. It's not going to be as easy as before. You have to find the antiderivative function or the potential function such that it takes the derivative. These three partial derivatives will satisfy simultaneously. This one, I can find them individually because taking derivatives, you don't have to hit any other components. Right? You don't need to worry about anything. Here, that's pretty different. I take the x derivative equals this one. I have to take a y derivative to equal this component simultaneously. That's not easy to find. Okay? So now I want to introduce a uniform way, and this way will be able to work for any given conservative value. So big goal is to find phi. So in order to do this, I want to finish this in 3 steps. Okay? I want to first fix the x derivative. Forget about the other 2. Okay? I wanted to first do the x derivative. Because I know phi of x is equal to y plus 2z. All right? If this guy is supposed to be equal to gradient of phi, which is equal to phi x, phi y, and phi z. Which means this is equal to my phi x, this is equal to my phi y, this is equal to my phi z. So if I have phi x is equal to y plus 2z, I know taking the partial derivative, y and z are both considered as constants. All right? I can find the antiderivative by regarding these two as constants. Can you do that? It's going to be xy plus 2zx, right? Here, the only thing I'm doing here is to find the antiderivative with respect to x by regarding yz as constant, right? Because yz is constant, finding the antiderivative, there's supposed to be a constant coming out, all right? So I want to call this as a constant p. Because y and z are both considered as constant, this is not a real constant. This is a constant depending on y and z. Would you agree with me? Because in this step, y and z are constants. So it is a constant depending on y and z, but not on x. Because x is the variable. I have a constant, but this is not going to be depending on x anymore. So this is the function I need to figure out in the second step. So the first step, I peel off the x dependent. Second step, I'm going to peel off the y dependent. In order to do that, I look at this equation. I take y derivative, where we have. I have x plus derivative of p, so py. All right? Yes, I'm taking the derivative with respect to y. Okay? I take the derivative with respect to y on both sides. Left side is partial phi partial y. Right side I'm getting x, nothing coming here, and I have a partial derivative of y hitting on p. Yes? And then I need to make sure this guy is equal to x plus 2z. Coming from here. So step 1 is to peel off the x dependent. Step 2 is to peel off the y dependent, which means I have to use this condition. Right? So if I use this condition, x plus py is equal to x plus 2z, this can only happen if py is equal to 2z. Right? So I eliminated x, I got py is equal to 2z. Then I know I want to find the antiderivative of of py with respect to y. Z is the constant. So p of yz has to be equal to 2 zy, but I have a constant coming out. This constant can only depend on z, but not on y anymore. All right? Because in this second step, y is the variable, but z is the constant. So I have a q of z. And this function can only depend on z, cannot depend on y anymore. Am I right? Yes? And then this is the second step. The only thing I need to figure out is to figure out what the q is. That means I have to take advantage of the z derivative. So this is my step 3. In step 3, I take the derivative with respect to z. If I take the derivative with respect to z, here my phi is equal to xy plus 2zx plus 2zy plus q of z.